Hello, my name is Urcan Altun, and I am a computer science student in Bilkent University. Today, I'm going to conduct an experiment on the conservation of mechanical energy on frictionless planes. The aim of this experiment is also to prove and inspect the conservation of mechanical energy on frictionless planes. In our experiment, potential elastic energy will be transformed into kinetic energy and potential gravitational energy on a horizontal frictionless plane and inclined frictionless plane respectively to inspect the law of physics given above. Before going into the details of my experiment, I want to talk about the theoretical background of it. First, let me introduce you to one of the mechanical energies that will be used in this experiment: kinetic energy. Kinetic energy is the energy of an object in motion, and as you can see here, it can be stated algebraically as like this. Another mechanical energy that will be used in this experiment is gravitational potential energy. Gravitational potential energy is the potential energy generated by the altitude of an object. It has a magnitude equal to the work done by the gravitational force on the object, and it can be stated algebraically as like this. Finally, the last of all mechanical energies that will be used in this experiment is elastic potential energy, which is a potential energy stored when a coil spring is compressed or elongated. It can be stated algebraically as like this. We will also use the work energy theorem to prove the conservation of energy theoretically. The work energy theorem states when forces act on a particle while it undergoes a displacement, the particle's kinetic energy changes by an amount equal to the total work done on the particle by all the forces. This theorem can be stated algebraically as like this. Moving on, by using these physical concepts, we can derive an equation like this for the first part of the experiment. This equation states that elastic potential energy transforms into kinetic energy completely, and from this equation we can derive a constant value that corresponds to the slope of the velocity with respect to the displacement of the coil spring. We will use this constant value to check the validity of our experiment while we plot our graph. The same thing can be said for the second part of the experiment as well. We derive an equation that states elastic potential energy transforms into gravitational potential energy completely, and from this equation we can derive a constant value that corresponds to the slope of the graph of the height of the object with respect to the elongation of the coil spring squared. We will use this constant value to check the validity of our experiment as well. So now we have talked about our theoretical background of our experiment. Now we can move on to the equipment that we will use for this experiment. The equipments we will use for this experiment are an air table and its accessories, a large sheet of white paper to put on air table to record the measurements, a scientific calculator, ruler with millimeter divisions, and a scientific scale. Now we have talked about the equipments that are used in this experiment. We can move on to the procedure of the experiment. First, we select a suitable coil spring and attach a known weight to its end. Then we measure the elongation of the spring due to the weight attached to its end, because we will calculate the spring constant of the coil spring by using the formula the applied force on coil spring is equals to the spring constant times elongation of the spring. Okay, then after we have calculated the spring constant, we will move on to the first part of our experiment. First, by using 3 adjustable screws, we level the air table in order to set the effect of the gravitation to its minimum value. Then we make sure that the air table is clean enough to make experiment on it. Then we measure the spring constant of the coil spring if it is not given, which is not given in this case, and we have already measured it. We place the coil spring at the side of an even horizontal air table, and then we compress the coil spring at different amounts with the puck and observe the transformation of energy from the elastic potential energy to kinetic energy when the spring is released. Then we calculate the average velocity of the puck at different displacements of the coil spring by using the spark positions. And then we record the values in a table. Well, we have ignored the first few data as the transformation of elastic potential energy to kinetic energy is incomplete at that time. Okay, then we make a plot of the average velocity of the puck with respect to the compression amount of the coil spring. So this plotted graph is expected to be linear, and we compare the slope of the graph to the constant value, as you can see, this constant value, which is the value that the slope of the graph is expected to correspond with theoretically if the total mechanical energy is conserved on the frictionless horizontal plane. So in the second part of our experiment, we place a wooden cube beneath the air table to give an angle of inclination to our air table. Then we again make sure that the air table is clean enough to make experiment on it. Then we compress the coil spring again at different amounts of displacement from its equilibrium position and observe how the coil spring pushes the puck upwards. The elastic potential energy stored in coil spring is transformed to gravitational potential energy at the end of this part of the experiment. So what I'm saying by saying this, that when the puck stops moving upwards and stops moving, we calculate the displacement and the height of the puck when it stops moving by using the spark positions and the angle of inclination. Then we create a table with the displacement and height of the puck at a given displacement of the coil spring from its equilibrium position. Finally, we make a plot of the height of the puck as a function of the compression of the coil spring to the power of 2. Again, this plotted graph is expected to be linear. We compare the slope of the graph to the constant value, this value that you see in the screen, which is the value that the slope of the graph is expected to correspond with theoretically if the total mechanical energy is conserved on frictionless inclined plane. Finally, I want to talk about the conclusions I have derived from this experiment. First of all, the purpose of this experiment was to observe and prove the conservation of mechanical energy of a system on a frictionless plane by transforming elastic potential energy of the system to kinetic energy and gravitational potential energy, respectively. In the first part of the experiment, a plot of the average velocity of the puck with respect to the compression amount of coil spring has been made. The plot was expected to be linear, and we have successfully derived a linear graph by using the taken data. We have created this graph to compare the slope of the graph to the value that you see on the screen, which should be the value of the slope of the graph theoretically. When we have compared the slope to this value, we have found an error percentage of 17.88%. In the second part of the experiment, a plot of the height of the puck with respect to the compression amount of the coil spring squared has been made to compare the slope of the graph to the value that you see on the screen, which should be the value of the slope of the graph theoretically. We expected a linear graph for this graph as well, and we have again successfully derived a linear graph with the taken data. When we have compared the slope to the value that we have just mentioned, we have found an error percentage of 2.3%. Okay. Error percentages are caused due to several factors for both parts of the experiment. For the first part of the experiment, one of the main causes of the error percentage was the puck's skew motion while getting thrown by the coil spring. When the motion of the puck was not linear, it was difficult to get the exact displacement of the puck between the time intervals. For the second part of the experiment, one of the main causes of the error percentage was the probability of spark meter not producing a dot at the point where the puck had stopped. Furthermore, the sign value of inclination might be inaccurate as well. For both parts of the experiment, air resistance might have played a part in inaccuracy of the actual values when compared to the theoretical values. Although air table was assumed as a frictionless plane, friction force might have still played a role in the air table, as it is very difficult to create a complete frictionless plane practically. Finally, spring constant of the used coil spring might be calculated inaccurately at the beginning of the experiment, thus leading theoretical value to be inaccurate as well. So that's all. Thank you for watching. Have a good day.